Hello everyone, I'm Zanchetta Jacopo, team leader of ProjectRED, a student team from the University of Modena and Reggio Emilia in Italy, based at the Department of Science and Engineering Method. Today, I have the pleasure of introducing you my team made up of more than 40 students coming not only from engineering courses but also science ones. Our organization is divided into 4 divisions: hardware, software, science, and business, each one led by a dedicated leader. Together with the team leader, the public relation manager deals with partnership relationships and finances, and then 2 coordinators supervises the technical side of our team, ensuring correct communication among the members. But moving to Project Red people, hardware is divided into 4 parts. We have the mechanics division led by Alex Fortuna, focused on the construction and development of our Sirio rover and its subsystems. Then Nicola Montanari leads the manipulator and effector design in its robotic arm division. And then the laboratory division is led by Tommaso Martinelli, which focuses on our laboratory organization, travel logistics, and the construction and crafting of useful structures such as test benches and our ground station. And then the electronics division, led by Victor Andrea Miselli, focuses on the design and development of our entire rover electric system and its subsystems, such as, for example, the safety system design. Then moving to the software side of our team, we have the communication division led by Paolo Casarini, which focuses on the motor control software design and the development of our communication protocol system. And then for the robotics side, we have the division leader, Frank Gemel Villanueva, which focuses together with the robotics division in the design and development of algorithms and interfaces to control our rover and its subsystem. Finally, for the technical side of our team, we have the drone division led by Alessia Rocca, which focuses on the development and construction of our new Nebula drone and its autonomous flying routines, and also its autonomous auto-landing safety system. Going to the organization side of our team, we have the business division led by Gianluca Lauro and Barbara Buccarello, which focuses on our partner relationships, on the development of our website and educational rover blog.
This year we participated to the IAC 2024, meeting experts from all over the world. Then in May we joined to the RoadTrack competition, a great experience that helped us learning a lot thanks to the amazing job of the FHNW team. But still, the ERC is the most significant event for us, not only because we can push our work to the limit and grow as a team, but also because we can share our passion with all the world.
The Zero Rover featured a simply buggy suspension with two V-shaped flanges pivoting at the chassis center. This year, we keep the core design but upgraded key element. The carbon fiber arm now mounted with glue and screwed flange, making assembly easy and more reliable in case of adhesive failure. We redesigned the fourth steerable wheel, now larger, stronger and better shaped for improved obstacle handling and terrain adaptability. The aluminum chassis platform mounted on the top of suspension still use square profile, but we adopt feather parts and also replace the single axe with two half shafts to cut weight and free up center space for electronic. The design is useful for fast chassis reconfiguration and adjustment. The differential bar is then made out of ultra lightweight carbon fiber and the suspension components are made from rapid carbon fiber. While the custom parts are produced using FDM 3D printing with PAS-XCF material, and the steering flares that require high precision and strength are instead printing using SLS technology with PA12. We apply topology optimization software to reduce weight while preserving structural integrity.
In the preliminary phase, the safety system was tested on the bench with a switch. The logic will be powered and will not be interrupted by the emergency button, ensuring that the signal with the ground station is not lost. The green button will activate the 22-volt power supply that power the motors of each system, and it can be interrupted by the actual emergency button. The safety system will be integrated into the PCB for the power distribution.
The rover traction relies on Maxon brushless motors. A USB connection is established with the first node, which acts as a gateway and facilitates master-slave communication with all other nodes on the CAN network. We utilize software provided by the company for the setup and tuning for the traction and steering motors.
The robotics division relies on Unity and Capella Sim to create realistic environments like the Mars Yard terrain of the competition. In addition, they allow us to simulate physics-based robot interactions and validate sensor data integration with autonomous navigation algorithm. Our rover is equipped with 4 steering wheels which will be controlled over the ROS2 framework. We developed flexible locomotion modes including crabbing, turn on spot, and swerve. Each mode can be dynamically activated based on the terrain conditions or the task requirements, giving our rover exceptional agility and adaptability.
To meet the specific needs of the European Rover Challenge, we designed and 3D printed custom components, including a camera support for optimal positioning of the vision system, a battery holder to ensure secure placement and proper weight distribution, and a propeller guard to improve safety during outdoor testing. These elements enhance both flight stability and system reliability during field operations. To support autonomous navigation, our drone integrates a vision-based system. During flight, the onboard computer processes the live video feed to detect Aruco markers in real time. The detection and pose estimation are implemented through ROS code, which extracts the marker ID and relative position with respect to the drone's frame. We also use Q-ground control as a mission planning and monitoring interface. It provides real-time telemetry, parameter tuning, and essential safety features. We can also upload predefined missions, track battery status, and verify system status during flight. Even if the test was not autonomous, it clearly demonstrated the drone's capability for stable liftoff, controlled flight along all 3 axes, and precise landing. We are now preparing to perform the same tasks autonomously as soon as the new components arrive. Also, the upcoming MATLAB workshops will support us in implementing and tuning the autonomous control algorithms. Software mechanisms via Q-ground control trigger automatic landing if battery is low or communication is lost. Additionally, the pilot can instantly cut motor power via physical emergency stop on the controller or activate the auto landing procedure. During the task, there will always be a dedicated pilot ready to activate the shown emergency procedure in case of necessity, as well as a second team member monitoring the autonomous flight operations and system status from the ground station.
This year, we redesigned the sampling unit, introducing a more compact internal storage case integrated with the driller, while keeping the external tray system, which still supports the sampling weighting and handling. The driller retains its tilt and the core mechanics is the same of last year, but is now fully 3D printed, improving flexibility, reduction weight and simplified production. We also introduced a modular science box system, 2 swappable units at the back, one for solid sample like sand and rock, and the other for the probes and liquid, with sensor for temperature, pH, humidity or P and conductivity. This update improved modularity, field efficiency and science capability.
The control of the driller is mainly divided into 2 parts. The control of 2 DC motor linear actuator wired with 2 shields placed on the STM32 and a stepper motor of the same type as those used for the robotic arms controlled via CAN Open protocol. The load cells communicates via I2C protocol with a module that acquires raw signals from the strain sensors. The purpose of this system is to simulate scales for both sand and rocks.
This year, we completely redesigned our 6 degrees of freedom robotic arm to integrate a new generation of stepper motors with built-in drivers that communicate with the Key Open protocol. We also simplified the mechanical structure, reducing the number of components by nearly 30%. All structural parts are 3D printed in-house, using ABS and PA60F. This results in an arm that weighs just 7 kilograms, offers a reach 1.5 meters, and can handle a payload up to 3 kilograms. We also developed a modular end effector with a universal base swappable TPU fingers to adapt quickly to different tasks.
ROS2 MoveIt framework is used for the autonomous motion planning of the manipulator together with collision checking and grasping procedures. We integrated an RRT planner with a camera mounted on the end effector, enabling us to get environmental awareness for the object's interaction. Rhythm for detecting the probes in the task so we can learn its position relative to the arm using a depth camera. This allows our manipulator to plan precise movements to interact with the probe, whether it's for retrieval or manipulation.